Uh, Good afternoon, good evening, good morning, everyone. Thanks for joining this webinar on predicting valve hydrodynamic noise using Autonomous Valve CFD. So whether you're a CFD engineer or a non-CFD, like a valve designer and valve enthusiast, valve manufacturer, this session is going to be catering all the sectors. So there is no prerequisite per se. So we'll cover from basics and things. So let me go ahead and jump into the topic. So before going into the webinar, I'll introduce the speakers and the contributors. So myself, Praveen Kumar, I'm the product marketing manager at Simulation Hub. So I have around 15 plus years of experience in CFD simulation in multiple domains. Now lately moved into product management and marketing side of things. And along with me joining, we have Akshay Dorle. He's the business manager and he's looking after the Autonomous Valve CFD business. And he has multiple years of experience in CFD simulation and a contribution from our young engineering team, Joel and Manas. So they are the CFD engineering team, like who helped in the content and contributing content. Yeah. So moving ahead, what's the agenda of this webinar? So we'll start with introduction to it. Why we'll see why it's important. You know, what's the big deal with the noise? Why we should be concerned about it. And hydrodynamic noise specifically, that is the topic today. So the physics behind it, and then we'll touch on the cavitation part. We'll see the connection, and then we'll see how to predict hydrodynamic noise. And what are the different methods through which we can predict the hydrodynamic noise in valves. And then we have a few case studies, and we'll close with the success stories, real life success stories, and then we'll at the end we'll take question and answers. So moving ahead, before going into the topic, for those who has joined new to the webinar series, who doesn't know who we are, what we do. So Simulation Hub is a AI-powered autonomous simulation platform. It's a cloud-based application, specifically CFD simulation application for different designers from different domains. To in the context of today's topic, so we have developed multiple applications for different domains. In the context of today's topic, it's autonomous valve CFD. More on that in further slides going ahead. So what's the deal with all the noise? So I always like to start with some facts or stats, so these numbers, I came across these numbers. So, so there you can clearly see, around 22 million workers are exposed annually to industrial noise, right? So, and another, like stats from United States of Department of Labor says around $1.5 million paid as penalties by US businesses for not protecting their workers from noise. Okay? So noise is considered as the next pollution, next serious threat after air and water pollution. So it is inevitable as we grow in industrially, it's inevitable. Like so noise will be there. How do we, deal with the noise? And there are some enforcements and regulations. So we'll see those. So there are, why valve generated noise is an issue because it contributes to potential hearing damage. So efforts are being made to eliminate those or keep them in limit. So legislations and company standards like OSHA and OSHA and EU directive in Europe and control of noise work regulations in UK. So there are different uh, standards and guidelines. So another thing is like noise generated by valves can contribute significantly to the overall plant industry plant noise. And not just that, it also damages the valves and surrounding equipment, connected equipment. Okay, so we'll see what like how and overall there is a typical guidelines for a typical continually operational control valves noise shall not exceed 85 decibel dBA. Uh, how it is measured like 1 meter downstream of the valve and 1 meter away from the valve, out of the valve. Okay. So what it feels like 85 decibel. So you can see on the left over here. So let me take the pointer. So you can see 85 decibel sound is something like this. And then it is a kind of at the border of no risk. And then when you go slightly above and even 1 minute of exposure to 107 is kind of risk, and it is high risk. Above 130, it's a high risk. So another interesting fact you can see on the right side table, it says like 85 hours, 8 hours of exposure, and you can see what is the permission exposure in 24 hours. So 88, just 3 decibel increase reduces the exposure limit, how long they can be exposed. So that limit by half. So that's how sensitive it is, right? Like 94 goes to 1 hour and then minutes and things. So this is just for a comparison. So 85 decibel is the limits that we have understood. So moving ahead, so noise in control valves. So there are three types of noise in control valves: mechanical vibration, due to the mechanical parts and the movements and things, and then aerodynamic noise in case the flow medium is gas or air, and then hydrodynamic noise caused by liquid turbulence, cavitation, or flashing. So this is our topic of interest today: hydrodynamic noise. And the source of hydrodynamic noise could be again, multifold. One is the turbulence itself, the flow turbulence, the flow separation, eddies, separation, and cascading. So all these energy converted into acoustic energy. So this is the starting point, but it's not very significant compared to the cavitation or flashing part, and also the mechanical vibration resulting from the turbulent flow, cavitation, and flashing again. So let's take a detour to understand what is cavitation so that you can understand the noise and things better. So it's a small detour, I would say. So on cavitation. So cavitation is nothing but bubble formation whenever and the collapse of bubble. So the vapor bubble, whenever there is a zone or a situation where the local pressure of the liquid goes below the vapor pressure of the liquid, then the vapor bubble forms and then it collapses when the pressure recovers downstream. So when the vapor bubble collapse, the bubble collapse, then it causes uh, severe damage to the surfaces, and it also creates a sound, okay, noise. So you can see in control valves, the vena contracta is the minimum area of flow stream where it is. So where the flow velocity will be high and the pressure is the lowest. So there, if the vena contracta pressure or any pressure goes below the vapor pressure, then the bubble forms and the bubble collapse when the pressure recovers downstream downstream the flow. Okay, so and what is caching? Sorry, what is flashing? Flashing is the outlet pressure is stays without recovering. It stays below the vapor pressure till the outlet. So that is flashing. So what are the impacts of cavitation? The material damage, as we already discussed, and the high noise and excess vibration. So this is the part I want to, connect back to the noise thing. So you can see the impact of cavitation is high noise and excess vibration. So in fact, there is no direct method experimentally or like in the test to measure the impact of cavitation directly. They are measured through noise and vibration. So if you take a test method. So they install accelerometer and then they measure the vibration and they record and they plot these graphs for different operating conditions, and then they come up with, okay, these are the different cavitation indices, which each index is like incipient is the starting point of cavitation where the small bubbles form in the flow stream. And then you can see constant cavitation is this point where the steady popping of the vapor bubble happens. So here the popping sound and everything that is connected, like that's the noise part. Okay. So, and then the choking cavitation index, all these things. So this index is nothing but a pressure ratio. So this is an indication where you are operating pressure ratio or cavitation index is uh, below or above the incipient cavitation. So if it is above, then it's in the non-cavitating, and if it is below the incipient cavitation index, it falls in the cavitating region. But there are different terminologies. For example, you will see in further slides XF being used. So it's just a reciprocal of that, and then accordingly the above and below part will vary. So I don't want to, explain more and cause more confusion. So we'll clear this out in further slides. So yeah, this is what I was saying. Like when you fall in this region, it's non-cavitating, and then when you fall below the incipient cavitation or above the in the reciprocal terms, like pressure ratio, you are in the cavitation zone. So as cavitation and noise are closely, connected, so all the mitigation steps or how to control cavitation are directly applicable to the noise mitigation as well. So how to control noise? There are two basic philosophies. One is the source treatment. You're addressing the issue at the source where it is starting, so the cavitation part. And the path treatment. Path treatment is nothing but managing the symptom. Once it is done, it's done. Now you're uh, you know dealing with the noise. So we'll see how. So the source treatment is, there are different ways to it. So one is making the flow pass through multiple flow paths. So this, how this will help? It will help us to shift the low frequency peak sound level to high frequency peak level. Like while high frequency sound, you can see when the flow flows through multiple paths, so it goes into the high frequency sound, so it's reduces. So that's the one method. So you can see on the right side, I pulled some examples of real valve, how they mitigate. So you can see from one of the manufacturer, it's mentioned single stage multi-hole. So this is what I was talking about, multi-hole. So this is one methodology, and they've written low noise and anti-cavitation. So it is one way to fight or eliminate, the cavitation and noise as well. The another way is like multi-stage. So here is an analogy, like kind of waterfall kind of thing. So high velocity and high noise, and then when you take it to through multi-stage, passing the same height or same pressure drop. In our case, so there are low velocity and low noise. So here you can see double stage, something like multi-stage, and high attenuation and low noise, right? So both noise and anti-cavitation. So the design is same. Once you control cavitation, then the noise is controlled. This is the source treatment method. And in path treatment, then you have multiple ways. You can add silencers or increase the pipe thickness. So each has its own impact and decibel control. So moving ahead, how do we predict hydrodynamic noise in valves in experimental method? So here is an example of the test setups, typical test setup schematic. So an echoic chamber is required. So to control the like sound dampening panels are there, and then you can see your this is the valve under test, and the valve under test, and there is a microphone or decibel meter which is positioned at 1 meter downstream the pipe and 1 meter away from the pipe. So at this position, they record and things. So this is a screenshot from FCRI test lab. So got from this paper. So you can imagine how they. So uh, what typically happens is, let's say there is a design requirement, and the design engineer designs the valve, and then a manufacturer like it they manufacture the prototype, and then they send it to the flow loop test like FCRI or Utah Water Research Laboratory, and then they test that a valve prototype, and then they get the flow performance report. So all this happens in a weeks of time or sometimes months, depending on the number of orders they have and number of valves to test in the testing facility. So this consumes a lot of time, as well as whatever they get out of the lab is report, but you get the numbers, but you don't get the insights. Why this number? Why I achieved so much cavitation index, or like incipient cavitation index is very high. So all these questions will may not be answered from the report. So report gives you the score, or kind of what is the capacity, flow capacity, or torque, or cavitation index, or noise. Like, that's it. So these are the challenges in flow loop test. So, like also there are resource limitations as well. So how large diameters can be, there is a maximum capacity for each lab to test the valves. So these are the limitations. And then each design iteration will take hell lot of time, the whole cycle, and the money involved. So what are the other methods? So here I'll invite Akshay to take over and to introduce the other methods. And Akshay, you
Yes,
can
Praveen.
share your screen, right?
Sure.
Yeah, thanks.
Just give me a second.
Sure. Uh, do you need any help? Like, would you like me to share the screen, or?
No.
Oh, okay.
Um,
Yeah. Uh,
Share it.
it's coming. Yes, we are able to see the screen.
Okay.
21. Yes.
Yeah. Uh, Sorry for that slight delay. So that was a fantastic introduction to the topic at hand, Praveen. Moving on to the methods of prediction of hydrodynamic noise. So the interest in hydrodynamic noise was tweaked due to the involvement of OSHA and also various other authorities, and they wanted to understand how to kind of predict this noise. So back in the 70s, there were independent bodies that were using some methods to uh, get some empirical formulas to predict this noise. And around the 80s, the international standardization of the valve prediction uh, was established. So this was IEC 534-8. And uh, around the same time, there was a German standard, which is VDMA 2422. So again, around 80s, around the late 70s, early 80s, these things were happening in the industry. And along with that, there was a scientific boost. So Lighthill, as we'll see in the next slides, was contributing to predicting noise through solving the governing equations. So we'll see how these standards along with some other methods like CFD can be used to get the prediction of the hydrodynamic noise. Moving ahead. So uh, starting with VDMA. So VDMA was came out with the procedure to predict the hydrodynamic noise in 1979. And in this equation, the hydrodynamic noise is basically dependent on two variables. As we have highlighted here, it is the CV, the flow coefficient of the valve, and Z. So Z is the differential pressure ratio at incipient cavitation or at the inception of cavitation. So as you see in this formula, XF is the differential pressure ratio and Z is just the same ratio at incipient cavitation. So having a dependence of CV and Z in this formula, it could be challenging for valve manufacturers because to predict the noise itself, you need incipient cavitation index, and you cannot get incipient cavitation index unless you actually measure it with the experimental setup as Praveen had discussed earlier. So this dependence is there. So there are two formulas. One is for non-cavitating flow. So even in case of turbulent flows, due to high-speed jets, due to vortices, due to flow separation, there could be uh, noise generated, and these equations can be used. Similarly, uh, I the IEC standards also came up with equations to predict hydrodynamic noise, again, both in non-cavitating and cavitating regimes. So both of these standards predict external hydrodynamic noise, meaning the one that is propagated uh, through the valve body and through the pipes. So it's dependent on the internal noise. It's also dependent on the geometrical factors. So these are known to the valve manufacturer uh, easily, the geometrical factors. The things that might not be so readily available with the manufacturer are the transmission loss and the internal noise. So we'll see how IEC, these equations from the IEC standards can be used to predict the hydrodynamic noise. So this is the basic flow chart, or just the major steps that you go through to calculate the hydrodynamic noise using IEC equations. As you can see, as we move from getting the flow rate, which could be easily measured, even the design factor, so which is the FD, it's in the hands of the valve manufacturer. But as we move along in the steps, uh, getting the jet velocity, then getting the acoustical efficiency, all of these parameters actually depend on sub parameters. So they depend on a parameter called as FL. You might have heard it is the liquid pressure recovery factor. Also, they are dependent on XFZ, which is the incipient cavitation index. And uh, in IEC standard itself, they introduced a term which is acoustical efficiency A eta. So this also varies depending on the Mach number of the flow. And so again, there are many parameters that depend on the design, on the internal flow, and there's a lot of dependencies that you must uh, know a prior to getting these hydrodynamic noise. So where does the role of CFD come in? So before jumping to the CFD methodologies, let's just have a quick introduction to CFD. What is CFD? So CFD is the science behind predicting flow, any transport phenomenon like fluid flow, heat transfer, mass transfer, chemical reactions. And how we do it is basically we divide the domain of interest in small volumes, which is called the finite volumes. And then we integrate the governing differential equations over these volumes and get the parameters of interest it could be flow rate, it could be pressure drop, it could be various other things, as we'll see in the further slides. So as we have already seen that even using equations from IEC, there's a lot of dependency, or there's a lot of parameters that manufacturers need to know beforehand to actually get the noise prediction done. So we'll see how CFD can be helpful in either predicting the entire thing without any dependency on the IEC equations, and how they can be used in a hybrid method. So starting with computational aeroacoustics. So this is one of the most complex ways you can predict noise. In this method, the dependence on computational resources and computational hardware and the time is pretty extensive, because we are resolving a lot, like a whole range of frequencies, and complex fluid phenomenon is captured. So it takes a lot of time to run these simulations and to extract the noise. But this is the hands down the best method that you can have to predict noise. It could be your broadband noise, it could be the broadband noise, or even the noise that is getting propagated in the domain, irrespective where the observers are. All of these things can be done with computational aeroacoustics. The caveat is it's very complex and time consuming. Then there are the integral methods. So one of the most popular method is the FWH method and the curls analogy. So in this, it's a compromise between the computational resources. So it's a sort of simplification from the CAA method. And in this, basically, what happens is you uh, predict the fluctuations of pressure in your domain, and then post-process the uh, information about the noise through these analogies, and through the FWH analogy or the curls analogy. So moving ahead, then there is one of the easiest method in predicting noise, which is the uh, broadband noise. So it doesn't require any fluctuating quantities. Just a normal steady state run can be used to predict the source of noise, and it also gives you a nice contour so you can visualize it. It doesn't require post processing of complex pressure fluctuating fields, and using FFT analysis to extract the frequencies from the fluctuating fields. All of that is simplified, yet you get insights. So the broadband model is used in these situations to have the prediction of the broadband noise. Now, as we have seen, the um, advantages of CFD, how it can be used to predict noise in the design stage of the valve itself. There are challenges in the conventional CFD approach. First is it needs an expert. So uh, the process is also manual intensive, in the sense it needs a lot of CAD cleanup, it needs fluid volume extraction, the mesh needs to be very good, and bad meshes needs to be dealt properly. There's also chances of solver divergence. So all of these things need to be taken care of. And then second, you can say cost is the HPC hardware. So you need a high performance computing machine in house to do these complex simulations, and the license cost to run commercial softwares on your systems again is an additional cost. So this is where Autonomous Valve CFD comes in. So it's a specialized app for Valve CFD simulation, and it's a virtual flow loop testing environment for you. So uh, it again uses the same standards for reference that valve manufacturers use to size their valves. And what we get as an output are CV, KV, CDT, and sigma. Sigma is the incipient cavitation index, which is very important as we have seen in the prediction of hydrodynamic noise. So is CV if we are using the VDMA equations. And this app is powered by three powerhouse technologies. So the viewer, the 3D viewer in which you interact with the geometry, is the Autodesk Platform Services viewer. Since the simulations are running on cloud, it's a web app. So all the simulations are run on cloud. No need for a performance infrastructure. So it's powered by AWS, and the solver behind all of these simulations is the OpenFOAM solver. So these are the three powerful technologies packaged in one for a very specialized tool called AVC. The workflow of AVC is pretty straightforward. As a design engineer or as a valve manufacturer with the design team, they just need a 3D CAD model of their valves, upload the valve, specify the flow directions, specify the openings. And once this is done, AVC will take care of all the conventional CFD methodologies or the CFD steps. And it's an autonomous workflow that we have developed. And what we get as an output is velocity contours. So where the flow is accelerating. So as we have seen, high velocity jets can cause a lot of noise. So you can visualize that and, optimize your trim designs accordingly. You can have a look at the flow lines, how the fluid flows through the different parts of your trim. You can have visualization of surface pressure. So where, there are zones of high or low pressure concentration, minimum pressure location. So this again is very important because this deals with the phenomenon of cavitation. So having insight into where this minimum pressure location is actually taking place becomes very important. And you also get quantitative data. So this was about qualitative data. You get also the quantitative data in terms of tables and a graph. And all of these insights are consolidated into a CFD report at the end of each and every simulation autonomously. So these are the valves that are supported in AVC. So almost all control valves from rotary to linear, even the isolation valves are supported. So just let's have a quick look at the demo. So have a brief introduction to AVC, how it works, and really get into how this platform helps you run CFD simulations. So we'll quickly run through this. So this is the dashboard of AVC. We just click on create simulation. It's a globe valve, so we'll start with the title, give it a brief description, and yeah. So there are 4 steps in CFD or AVC. First is inputting the CAD model. You upload CAD model in, say, step file, .sat file, parasolid file. Then we specify the wall. What's the size of the wall? What's the motion type? The valve roughness, and all of these things. Next, we move to the moving part selection. So we quickly select the moving part, the actual plug that will move. Then we select the axis of lift, and it automatically creates all the openings for you. You can even tweak those openings. Once that is done, so this is a advanced user option, which actually helps in capturing all the minute details in case you're designing an anti-noise shield or an anti-cavitation trim. So all of this feature will help in capturing these. So the next is uh, specifying the flow direction, and that's it. So once we submit the run, all the conventional CFD processes are taken care by the AVC platform. It will do all the fluid volume extraction, meshing, solving, and even post process the results for you. Now, this is once the simulation is done, this is the post process environment. So here you can visualize the streamlines, how it's flowing through. How the fluid is flowing through the each individual hole, and how it's interacting with the various surfaces. You can check the different angles of openings. I'll quickly move ahead. You can even change the field variable. So earlier we were seeing velocity, now we are seeing pressure. So that was about streamlines. Next comes the surface pressure. So again, locating your high pressure locations. As you can see, here is the high pressure location, uh, and where the low pressure zones might be. You can visualize them pretty effectively with the surface pressure tool. Next would be the contour plots. So this gives you an insight into how the fluid moves inside the valve. It gives you zones where you can focus in terms of acceleration of the fluid, which will form jets. As you can see here, it's forming some nice jets, and where it might be stalling, where it might be recirculating. All of these things can be visualized. I'll quickly zip through this. Again, we are visualizing the contours. Give it a second. Seems like it's stuck. Give it a second. Okay, stop sharing. Seems like it's stuck somewhere. Uh, yeah, okay. I've got it working. Give me a second. We'll quickly zip through. Is my screen visible? Sorry.
Not yet, actually. Yeah, it's loading. Yeah. Yes, we are seeing the first slide. Yeah, now the demo video is getting.
Quickly zip through this. Praveen, if you are
Yes,
able
actually,
to,
I'll do that. I'll do the
yeah,
screen
thank you.
sharing. Just a minute.
Yeah, it's visible, Praveen. Thanks a lot. So we were at yeah, we had visualized the flow. Now we'll have a look at the quantitative data. So as we saw, we'll get it in forms of table and also in terms of plot. You can export it in terms of CSV or an image and have a look at the graph as well. Again, you can export it to a CSV file or an image file. You can use it in your reports. And so we have seen the qualitative part, we have seen the quantitative part, and now we'll see how everything is consolidated in a report. So this is the report that is generated at the end of each simulation. So it gives you a detailed description of the valve details that we had selected in the first stage, the executive summary, which details all the results and all the plots in terms of tables and graphs. Then we go into the CFD methodology, give a brief description about the various stages in CFD. Then we have the look at the quantitative results and then the qualitative results. And also there's the table for incipient cavitation index. So which is again very important to uh, predict the hydrodynamic noise. So moving on to case study. So as it's a ritual of every webinar that we've done, we also have a case study for uh, this webinar as well. We have, uh, let's have a look at the case study that we have done. So this is a globe valve, and we used the Prodman model, which is the simplest model to implement, which gives you a nice contour so you can visualize the source of the noise. So all the red zones is where there is a lot of noise being generated, and this will be propagated out through the valve body and through the pipes and even in the downstream direction. So in this case, what we have done is this is for the full opening of the valve, and we tested or we predicted the hydrodynamic noise for three different process conditions. One is when the flow is turbulent and not cavitating, one where it's very close to cavitating, which is the incipient cavitation range, and in the third, which is the bottommost, it's cavitating completely and it's not flashing, but it's also in the cavitating zone. So with this, what we observe is as the flow regime shifts from turbulent to cavitation zone, uh, the maximum noise that you can see from the red color values goes on increasing. And to validate the CFD or to see how close or how good this prediction could be in terms of real life applications, we also did a quantitative study. So if we have a look in the next slide, so this is the quantitative comparison of the different methodologies we used to predict the hydrodynamic noise. So we used the equations that we saw in the earlier slides, which was VDMA. It's dependent on CV and XFZ, and also the complex IEC equation. So again, getting values from IEC took a lot of time because there are a lot of dependencies. We have to calculate FL, we have to calculate various parameters that are interdependent, and with this complex formula, we were able to get a graph for the cavitation or the hydrodynamic noise. So in this graph, what it depicts is after the XFZ, as I've shown in the plot, which is the incipient cavitation location, or the inception of cavitation begins, or the cavitation starts here. So after this, there is a drastic increase in the sound or the noise generated by the valve. So this is evident from the uh, phenomenon of cavitation. So as we have seen in the slides, with uh, the pressure ratio or differential pressure ratio increases, so the uh, likelihood of cavitation also goes on increasing, and this is depicted by the increase in the level of noise. So on the uh, left hand side column, or the left hand side axis, it's the sound pressure level, which is in dBA. So that A at the end of dB is a filter, A weighted filter that is used in industry to uh, in the measurement instruments to get the noise values. So we have again used the same units. The yellow dots that we see are the CFD results. So for the turbulent zone, we can see before XFZ, there is the noise predicted by the Rodman model is slightly higher. So this is fine because we are not considering the transmission loss, or it's the internal sound. It's not exactly the external sound propagated, but it's a very good estimate because this internal sound itself will propagate outside. So with some adjustments to it, we can definitely get uh, uh, the required predictions. And in the cavitation zone as well, we see that we are slightly over predicting with respect to IEC. Again, this is evident because it's just the internal sound, and some of it will be dissipated by the valve body and the pipe thickness. So this gave us a very good understanding of how formulas and CFD can work together to predict hydrodynamic noise in a much easier, much quicker fashion. So uh, that's about it.
Okay. Thanks, Akshay. And then from here, I'll take it over. So we have like the workflow of the app is very simple, right? But we need to make sure all the results what the app delivers are right. So we did some validation study. So not some, lot of validation studies, including test data from FCRI and UWRL. And our observations are in most of the cases, it falls in the range of plus or minus 5 percentage, accuracy. So upper deviation, and so you can this test or validation studies cover a wide range of size of the valves, that's the flow capacity, and different types of valves as well. So this is for the CV and CVT, but we have also done few validation cases for the incipient cavitation index and FL. So you can clearly see these are the test data from a paper and research paper, and then the those are plotted against the CFD results, and we are able to see above 90 percentage, accuracy matching with the test data. So you can see the same CV and incipient cavitation index are being passed on to the VDMA methodology. So once these are made sure, then the noise calculation is as per the standard. So that is also, ensures the values are right. Okay. So moving ahead, there are a few features to support the complex anti-cavitation trim designs, and also the features which shows the incipient cavitation index table separately. So these are recently added things in the software. And with this, we support a lot of complex features from, these are a few examples from the internet. So all sort of complex shapes, trim shapes we are able to support. And I'm presenting one interesting case where we're able to, how we are able to reduce the time to market. So this was before the simulation of AVC. So the CC Tech parent company, we were like, we had a engineering service team who provides CFD consultancy services for the different companies, different industries. So this was one of that case. So where we took for a globe control valve with cage, it took as almost 7 weeks time to come up with the complete results, and the same case we are able to do it within an hour in using AVC. So how is that possible? What happens, like what happens behind the scene, right? So how did we trim the time? So what happens is, when we input the valve design to AVC, so it assigns a dedicated 36 core Amazon EC2 instance, and then all the CFD processes are done autonomously on the cloud. So simulation of APIs are called for cat cleanup, meshing, and solve, and then you get the simulation result fetched and displayed or like viewable on the browser. So you get all the this is incipient cavitation index actually, and then CV, CDT, all those things. So this is not just for one opening. So you get at the same time for all percentage of openings, same process happens parallelly. So at the end of 1 hour, you'll get the complete capacity as CV curve, CDT curve, and index information for the whole range of operation. And it's not just that. If you have multiple design options, let's say you have multiple design trim designs to mitigate cavitation, you can upload all of them parallelly and get the reports, insights, and everything, in the same time span. So it typically takes 1 to 2 hours of time, depending on the complexity and size of the valve. And it doesn't end there. People or your design team from multiple geographical location, different branches, like different office space, can contribute, collaborate at the same time. They can run a different series of valves at the same time. So this is how you can leverage the power of autonomous and cloud computing together, right? So a short comparison of conventional method, where completely the manual process, and it is limited by the in-house resources and the licenses and part. It takes more time. And then on the contrary, like we have simulationHub. On the other hand, the processes are autonomous. The cloud computing you can leverage, and the results are available in hours. So moving ahead, I would like to present in this webinar with one real life customer success story. So these are our customers worldwide, leveraging AVC in their design cycle to optimize and verify their design and optimize their designs. So Bray, I'll pick Bray as a customer success story for today's webinar. So Bray International is a big valve manufacturer from North America. It has offices in different places, and it has design centers in Houston, Bangalore offices. So The challenge they had was the flow loop tests they conduct. It involves manufacturing a prototype, and it takes 3 to 4 months of testing each valve design. And the on the contrary, they already had expert team and the CFD tools, the conventional CFD tools. But the problem here is they were limited by the number of licenses, and the CFD experts were overworked. So there are a lot of projects in the queue. So large work backlog of designs in queue. So that is the challenge, and it usually takes a week's time or 5 days, and the machine is completely engaged, the license is engaged. So the process has to go in queue, like one opening and then the next opening, then you get the complete CV curve. So now after autonomous valve safety, what happens is, Bray has been our enterprise customer since 2019, and for the last 5 6 years they have been continuously using the application. So at the start there were 3 users, and now it has reached up to 30 different users. And it's kind of it empowered valve designers themselves use CFD as a tool to view the like CV and CDT curves and incident cavitation index. And what happened is the CFD in-house CFD team, the expert CFD team, they had got time to look at high fidelity simulations, even higher, like similar to aerocaustics or much high fidelity simulations and erosion, that kind of thing, very multi-phase deep analysis. So that's how it helped to accelerate their design verification process and to arrive the optimum design in very efficient time. So we also visit the customer team and conduct workshops and trainings regularly. So after sales support and everything is provided. So these are some kind words from Brindesh, Mr. Brindesh. He's the EVP and CMO CTO of Bray International. So yes, with that, there are few more case studies. I'll considering the time, I guess we'll move to the end of this. So what's next? You can log into simulationhub.com and directly start your trial subscription plan. You can activate it and experience the uh, you know AVC app, or you can schedule a call with our expert. We'll schedule a personalized demo to your team, understand your custom requirements, and cater them as per need. So yes, and exclusively for these webinar attendees, you can schedule the call and mention about this webinar attendance, and then you will get 1 month free subscription instead of 15 and more simulation credits. So that's what you can do. You can go ahead and schedule the call. You can find the links on this website to request a demo. Okay. So with that, we are at the end of this session. So let me see the questions. In. Okay. Okay. So we had few questions already personally answered, but still I'll just answer. I'll just read out so that others can also get the answers. So there was some question about can we do FSI simulation and predict airborne noise with AVC? Rizwan, currently we do not have the capabilities for performing FSI simulations in the app, but however, the simulation of team has the CFD expertise to perform such simulations, and we can take it on a project basis or something. So we can connect and check your requirement and see how we can cater those things. So can we have the link for recording? Yes, yes. We will be you'll be receiving the email in a couple of days after this webinar with the recording links and so and at any point of time you can connect with us and we'll be happy to connect with you and clear your questions. So does anyone have control over solver parameters that open form users. So I guess Vinita is, I guess, like from the CFD side. So I myself was a CFD engineer. So I know it's kind of hands tied, right? Like, there you don't see much of controls on meshing parameters or the CFD parameters. So yes, we do have two modes. One is the autonomous mode, which is intended for valve designers who is not, like, very exposed or aware of CFD process and things. The other one is the expert mode. You can activate that, and you'll get more control over turbulence models and certain parameters, numerical schemes you can do. And on top of that, what we do is, if your organization follows certain SOPs or certain protocols, like what uh, uh, numerical methods, or what kind of models works for you best, so we can also fine tune it or do the settings only for your organization. So even that kind of things are also possible. So yes, I guess that covers the numerical schemes as well. So that is possible. Okay, so another uh, uh,
Shashank has asked a question.
yes, yes.
What is the status of finding the aerodynamic noise values? Because that has more noise than hydro. So Shashank, I would like to answer that question. So right now we have started with hydrodynamic noise because as the physics is kind of uh, not as complex as the aerodynamic case, we have started with hydrodynamic. And for aerodynamic, again, this can be done on a case-to-case basis. Uh, but yeah, as of now, it's a bit tricky. Praveen, if you would like to.
Yeah. So as Akshay said, we started with hydrodynamic noise and then things. But aerodynamic noise is, it's a bit more complex and things. So right now we can take on a case-to-case basis, but it's in the roadmap, but not, immediate things. So again, connected question from different uh, attendee. So hydrodynamic noise prediction will be part of AVC, and when it will be available. Okay. So right now we are providing incipient cavitation index and the CV. So the other things what Akshay showed are a work in progress thing. So the broadband noise prediction, the contours, and the calculator for calculating the noise, hydrodynamic noise. So some calculation feature is being worked out. So meanwhile, what you can do is, like, you can, once the simulation is completed, you can raise a ticket, and our team can generate it using the backend, features. So it's not yet, it's in the testing platform. So it will take maybe another month or two. We will see how it goes, and then you will have a press release and things for those things. Yeah, yeah, release notes for this feature. Yes, thanks for asking that. Uh, So we are already spilled, 5 minutes more than what we expected. So I would like to take all the other questions. We'll email them, answer them separately through emails, and also feel free to reach out to us on simulationhub.com, and then you can request a demo. So thanks, Prakash. He's saying interested in recording link and PPT. Yeah, we'll email you. We got your email ID, and we'll do that. Yeah. Thanks everyone for joining. Thank you. Thanks, Akshay, and thanks, Joel and Manas, for making this webinar, very interesting. Thank you, everyone.
Thanks a lot. Have a nice day, everyone.